this surface is actually on the plane, it's flat. So by this formula, we express a complicated integral over a very complicated surface, which could be very curved, like a sphere or part of a sphere, as an integral over a domain on the plane, which is flat. So that's the definition, which we talked about last time. And then in some special cases where, for example, your surface is a graph of a function, we have some, the formula simplifies, and we have various formulas which kind of give us a shortcut to the answer. Okay? So finally, we are ready to state the Stokes theorem by using this notion of a surface integral. Okay? So let me draw this one more time. So you have this our surface M, and we have the boundary, the circle boundary, which I'll call B of M. So on the right hand side of the Stokes formula, we will have a line integral of a vector field over this boundary. So we'll have a vector field F, which will be defined in three-dimensional space. In particular, will be defined on this entire surface. And on the right hand side, we'll simply take the line integral of this vector field over the boundary. Okay? So this is something we learned before, so I don't have to say much about it. This is just what has become by now the usual thing, the line integral of vector field, which is, again, to calculate it, we need to parameterize the curve, and then there's a very simple formula which allows you to take this integral. And now, on the left-hand side, we're going to have an integral, which is a double integral, and it's going to be an integral over M. Okay? And then the integral, it will be the integral of another vector field, and that vector field will be nothing but the curl of F. Curl of F. So you have your vector field, and it appears on the right-hand side. But on the left-hand side, you have another vector field. This is something which I was denoting by E in all my previous formulas. So we have double integrals of a vector field E over surface. But now take as E the curl of your original vector field, which is given to you from the beginning, F. F is given, take its curl, that's another vector field, and take the integral of the curl. And so the remarkable statement is that you always have this equality. You have this equality of a double integral and a single integral over surface and over the boundary of the surface. Now, what I have said is still incomplete. And the reason it's incomplete is that both of these integrals depend on choice of orientation. Did you have a question about this? Well, curl of F would be what I call here E. Right? Right. So I purposefully called this vector field E, and I call that vector field F. Because on the left-hand side, when we do the double integral, we're actually integrating not F, but curl F. So that's why I'm using a different notation here. So it's not confuse you. We are given a vector field F, but we are sticking that vector field on the right-hand side into a single integral, into a line integral, right? Whereas on the left-hand side, we do curl. And curl is another vector field which we know how to calculate. And today we'll actually see what the meaning of that curl is. We'll get a better explanation of what the meaning of this vector field is. Okay, so that's the formula. But as I said, on both sides we have two integrals, which as I explained, requires the choice of orientation, right? So in other words, depending on how I choose orientation on M, I will get plus minus some answer. I'll get some answer or it's negative. And if I want to pin it down, I have to say which orientation I should take. Both integrals are well defined. There's no canonical choice of orientation, right? There's no canonical choice of orientation. So there are two possibilities, and there are two possible answers. They differ by sign, but I have to say which one I should take for this to make this well defined. Likewise, here I also have two different answers. In the case of hand, I have the circle. I can choose orientation which goes, counterclockwise or clockwise if you look from above. So again, there are two different answers which differ by sign. If I'm saying that these two things are equal to each other, I better be precise and say how the orientations should be defined so as to make this into an equality. Because if I make the wrong choices, instead of getting this formula, I'll get this equal to negative of that. In other words, if I wanted to be careless about orientation, I would not be able to state this formula at all. The best I could do, I would be able to say this is equal to plus minus this. And then if I did that, I should be fired. So we don't want this to happen. Well, maybe you do, but I don't. So that's why I'm going to explain how to choose orientation so that we don't have this ambiguity. And of course, the point is that you probably guessed already because this is very similar to the problem which already arose when we talked about the Green's theorem, which is actually kind of a little brother of the Stokes theorem. We'll talk about it in a minute. In Green's theorem, there's also this issue of orientation. And the way we handled that was by saying that was the following. Let me do it here. So you see, in Green's theorem, we also have a two-dimensional region, but it was flat. This is flat. This is not flat. Well, I have drawn it on a flat blackboard, but it's 3D. I was just reading about this new movie, Avatar. It's going to be in 3D. So I was thinking, maybe some years from now, these lectures I calculus will be given also in 3D. So you will all be wearing these cool glasses, and you will actually see this three-dimensional. So I'll be able to draw three-dimensional surfaces. I should talk to Cameron about this. I'm sure he's a huge fan of multivariable calculus. So, or if he isn't, he should be because he uses a lot of special effects. And of course, how can you do special effects if you don't use calculus? Anyway, so in Green's theorem, you have a region like this. And the way we handle this is we said, once you have this region, the orientation you define on the boundary is such that when you walk on the boundary, the region is to your left. Okay? If you walk on the boundary, the region is to your left. So it will be like this. It will be counterclockwise in this picture. So I would like to say the same. I would like to say that if I walk on this boundary, if somebody walks on this boundary, then the region should be along the orientation, with respect to orientation. The orientation should be such that as somebody walks along this boundary, the region itself, the surface is to the left. But the question is, how do you expect that person to walk on this? There are two possibilities, right? It could be that they walk like this, or they could be walking from the other side of the blackboard. You see, a priori there is no choice. I mean, there are two choices a priori, right? There is no canonical choice. There is no given choice. In the case of a plane, we do have an obvious orientation. We do have a special orientation, and the reason is the following: because there's an orientation which kind of sticks out towards us. Another way to say it is that there is an orientation which we call K. We usually draw this coordinate system, which is I, J, and then there is a K, which is obtained by the corkscrew rule, the orientation, the right-hand rule, whatever you call it. Remember this picture? This was one of my fondest memories of this class. This discovery of this visual aids. This is how you show the normal. So the point is that you can't just say, since I can actually move this, you can already appreciate the problem in giving it orientation. Orientation could be like this or it could be like this. But the point is, when we actually draw something on a two-dimensional plane, we look at it from a certain direction. We have to be looking at it from a certain direction. We either are on this side and we're looking on this side, or we are there. And let me tell you, there's not a whole lot of space behind that board, so we should be on this side, right? Once we are looking at it from this side, we can give it any coordinate system, any orientable coordinate system. In fact, this is not even canonical either, but I can rotate it and so on. But whichever coordinate system, x, y, I choose, the cross product of the I and j will be looking in this direction, will be sticking this way. So that's why when we have a region on the plane, we actually have canonical orientation. And that's what we call vector k. K being the cross product of I and j. In this order, first x, so this is the unit vector in the x direction, this is the unit vector in the y direction. We take the cross product in this order, right? And so that's what gives us this z, the z-axis, or the unit vector along the z-axis. So we're kind of lucky in this case. We don't have to make a choice. The choice is made by the fact that we're actually observing it in a certain way. We're looking at this blackboard in a certain way. But if we have now a surface in a three-dimensional space, for example, I could just put this blackboard somewhere in the middle of this class, and some of you will be on one side, and some of you will be on the other side. So for some of you will be looking from one direction, some of them will be looking from the opposite direction. So some of you will do one orientation, for some of them it will be natural to take the other orientation. You see, so in general, there is a choice of orientation. But once you make that choice, if you make it like this, you can say, if a person walks so that their head is, points in the right direction, up, then the domain is on the left. Then it actually makes sense. So somebody could be walking like this, their head would be this way, right? And so they will have the region on their left. So that would be, we get the old rule. If on the other hand, I would just say, let's choose the other orientation, which goes in that direction, I would still have the notion of somebody walking along the boundary, but that person would be on this side, right? And then it would still make sense to say that the region is to their left, which would then mean the opposite direction. Well, you have to believe, trust me, that this is how it works. But you can just imagine it. If it were made of glass, you will see it, right? So the rule in general is like this. If a person is walking along this, pointing in the direction of the orientation, if this is your orientation, and you're not upside down, you have to be, oriented in the right way. Your head should be above your feet, basically. With respect to this orientation, I'll try to not to make too many jokes about this, but I'm sure you can do them yourself. So if you walk this way, the surface should be to your left. So this is how it works. And if I chose a different orientation, which would be inward, then I would have to draw this little fellow pointing in this direction, and then it would have to walk so that the region is on to the left. Okay? So that's the rule. Is that clear? Okay, so this is pretty clear. So that's the rule I choose. If I choose that rule, which it will give me a consistent formula, it will give me a choice, whatever choice I take here, once I make the choice of orientation n, I get orientation on the boundary as well. And it is for these two choices that these two integrals will be equal to each other. So that's the statement of Stokes' theorem. Now, the next thing I would like to do is I would like to kind of try to demystify this formula, because at the moment it looks pretty bizarre in a way, because you have two different types of integrals. So one of them is of the vector field, the other one is curl. Okay. So what I would like to do is I'd like to explain how this formula actually fits in this general principle, which I talked about earlier, okay, of which we have now seen several examples. So I would like to convince you that this formula is actually a special case of this general principle, just like the fundamental theorem of line integrals and the Green's theorem. So that's the next thing that we're going to do. So in order to explain this, I would like to actually give a slightly more precise formula for a surface integral. And so this is going to be a slightly long and somewhat boring calculation, tedious calculation. But bear with me, because at the end of the calculation, I hope that I'll be able to demystify this formula, and you will see that really it is part of a pattern, which is much more, how should I say, much more convincing. Okay. So the first thing I'd like to do is I want to go back to general surface integral, like this. So here E doesn't have to be the curl. It could be some vector field. And I'd like to write a slightly more explicit formula for it, assuming that I have a parameterization. So let me recall what I wrote in the top right corner there. I wrote that this is equal to the integral over d, the parameterizing domain of E dot RU cross RV. Where RU and RV you have, well, the beginnings of RU and RV you have on that blackboard. So now I want to actually calculate RU cross RV for you. Okay? So I'm going to calculate what RU cross RV is. So this is just the usual cross product. This is just the usual cross product where I put dx, du, dy, du, and dz, du in the first row, and I put dx, dv, dy, dv, and dz, dv in the second row. Okay? So now I just write down what it means. So let me just start with I. So this is going to be dy, du, dz, dv, minus dy, dv, dz, du. This is times I. Okay? Maybe here plus. So now j. So I have to look at this, and I have to remember the sign. So it's going to be dz, du. It's going to take a little time. So, but you will like it when it's over. Trust me. So it's worthwhile. It's worthwhile to do this calculation. Dz, dv, dx, du. J. I have to do it once to believe it, and then after this, a lot of things become simpler. Plus, finally, I have to do the k, and the k is dx, du, dy, dv, minus dx, dv, dy, du. Okay? Check this. Okay? Are you with me on this? Is it good? You can only, if you agree, then you will not have a chance to disagree with me later. This is your last chance. Okay, so if we agree on this, have you ever seen this formula before? You're under oath. So have you ever seen this formula before? What is it called, this kind of expression? Come on. It starts with a J. It's a Jacobian. Okay? It is a Jacobian for the coordinates y and z with respect to u and v. This is a Jacobian for the coordinates z and x with respect to u and v. And this is a Jacobian for x and y with respect to u and v. Is that, everybody agrees with that? So I actually can rewrite this in a more compact way by using the notation which we introduced when we talked about Jacobians. Okay? So this is a notation for the Jacobians is d, you put a del like this, and then you put y and z over del of xy, uv. This is a notation for the Jacobian, which we have used extensively about a month ago or so. Okay? So this is times I, plus we have the Jacobian for z x over uv, j, plus the Jacobian over xy uv, and then you put k. So this is actually the explicit formula for this cross product. And this cross product enters in the definition. Okay? So now let me actually take the dot product so that I get the entire expression. For this, I have to also say what is E. So let's say that E is AI plus BJ plus CK. Then what do I get? I get E dot RU cross RV, which is my integrand in the surface integral, is A times D times this Jacobian plus B Okay, so that's the formula. Here is actually explicit formula for what you should integrate when you take double integral vector field. Explicit formula, which is written entirely in terms of the components of your original vector field and the Jacobians of the coordinate change from uv to all possible pairs of coordinates amongst x, y, z. Now, how can you remember this without memorizing this formula? It's very easy. So first of all, you have a, b, c. Right? These are the components of the original vector field. And then you also have x, y, and z, the three coordinates. So you have to remember the structure of the formula. That there are three terms. Each term corresponds to one of the three components of the vector field. And then you have to remember which Jacobian to put. You see, there are three different Jacobians. But there is also a subtle point, which is in the Jacobian, you also have to remember in which order you put the coordinates. You may remember from doing double integrals by using general coordinate changes that if you switch the coordinates, the Jacobian gets a minus sign, right? Jacobian gets a minus sign. So here it's important that I put yz over uv and not zy over uv, right? So first thing you notice that if you take a, the variables which get involved, so a corresponds to x. So to get the variables involved, you have to cross it out. So you see, you have a, y, z here. Then you have b with xz and c with xy. So that the two coordinates which you take, which appear in front together with the component of the vector field, are the remaining two components, right? So a is the x component. So the coordinates which are relevant to this term of the formula are y and z. And then you have to ask yourself in which order. And the order should be what mathematicians call cyclic order, which means this is first, this is second, this is third, this is fourth, and so on. So it kind of goes in a circle. So for example, y and z have to appear in this order, y, z. But z and x should appear, you're at z. What's the next one? The next one is the first one. You kind of, it's a cyclic order. Okay, so it's like zx. And then like x, y is clear. So x, y, y, z, zx. And then you put the remaining component of the vector field. So that's what the meaning of this formula is. Okay? So that's the first thing we should agree on. The double integral can be written in this form. Okay? But now let's go back to Stokes' formula. In Stokes' formula, there is an additional complication, as if this formula was not complicated enough, right? We actually have to take the surface integral not of the vector field itself, but of its curl. So gee, we have to do one more cross product, right? But actually, the funny thing is that when you do that cross product and you combine it with this stuff, which you can imagine is going to look horrible, right? Actually, it will look better in some sense. In other words, you'll get something which will have a much more conceptual explanation. So let's do that. Let's do that because I promise that I will explain it to you. So let me explain this to you. So we're halfway there. What we need now is we need to apply this formula to the left-hand side of Stokes' theorem, where we're just doing it to the curl of the vector field and not to vector field as before. So if E is curl of F, then what does it look like? So we have to again do this. I, J, K, then we put ddx, ddy, ddz, and then we put pqr. So what do we get? We get dr dy minus dq dz times I. Plus dp dz minus dr dx plus dr dx minus dp dz. But please check that I did it correctly. Dr dz, because if I mess up one term, then it will not come out. Right. So okay, good. That's right. And in fact, for good reason, because this is expression in Green's theorem, right? So we know that Green's